Hook. The most advanced AI model you've ever used wakes up tomorrow as a complete stranger, with no memory of past interactions. This isn't just a gap in memory, it's a silence where a relationship should be. This is a structural problem, not a model size problem, because even the largest models will forget everything if they don't have a mechanism to retain and recall information. This limitation stems from the fact that current AI systems are designed to process information in isolation, without the ability to learn from past experiences and retain a sense of identity. Why context windows fail as memory? Using context windows as a form of memory is inefficient and ineffective. From a token cost perspective, a user with 6 months of history costs more on a single message than a new user costs in an entire week. This is because the model must process the entire conversation history, which can be computationally expensive. Furthermore, context windows suffer from the discrimination problem, where a passing comment about coffee and a hard compliance constraint receive equal weight in a transcript replay. This lack of discernment leads to a model that is overly sensitive to irrelevant information. Additionally, when a fact changes, both old and new versions coexist without a signal for which is current, resulting in confusion and inconsistencies. Human memory, on the other hand, encodes information selectively, consolidates it over time, retrieves it contextually, and forgets aggressively, making it a more efficient and effective model for information retention. The 5-stage pipeline. To create a more human-like memory system, we can use a 5-stage pipeline: capture, consolidate, retrieve, reconcile, and decay. In stage 1, capture, we use a memory class enum to classify information as ephemeral, durable, or expiring. The classify_for_capture function determines whether a piece of information is worthy of capture, using 3 tests for durability, relevance, importance, and consistency. For example, a comment like "I'm frustrated with this bug" should never reach long-term memory, as it's a fleeting sentiment that doesn't provide valuable information. This rejection system ensures that only relevant and important information is stored. In stage 2, consolidate, we address the deduplication problem by collapsing multiple instances of the same preference into a single confident entry. We use a similarity ratio, _shares_subject check, and contradiction detection to ensure that the store doesn't bloat with redundant information. Without this stage, the model would become increasingly inefficient as it accumulates more data. In stage 3, retrieve, we use a composite score to retrieve relevant information. The score is calculated as 60% semantic similarity, 20% freshness, 10% reinforcement, and 10% confidence. This ensures that the model retrieves information that is relevant, up-to-date, and frequently accessed. Returning a small number of high-quality memories, such as 5, is more effective than returning a large number of low-quality memories, such as 20. In stage 4, reconcile, we address the problem of changing information. When a user changes their job title, for example, we use a supersede versus coexist versus flag_conflict logic to determine how to update the information. The flag_conflict branch is the most important, as silently picking the wrong side can lead to the model acting confidently on stale information. In stage 5, decay, we implement a mechanism for forgetting information that is no longer relevant or useful. Systems that never forget become indistinguishable from systems that remember nothing well, as they accumulate unnecessary information. We use a resistance formula, where frequent access slows decay, to ensure that the model retains information that is still relevant. Information that is no longer accessed is archived, but not deleted, allowing for potential recall in the future. Assembling the engine. The 5 stages compose into a memory engine class, which processes turns, retrieves information for queries, reconciles and applies updates, and runs maintenance tasks. The process_turn function triggers the retrieval of relevant information, which is then reconciled and applied. The run_maintenance function ensures that the model's memory remains up-to-date and efficient. What this changes? Memory engineering changes the way we approach AI development. Prompt engineering focuses on what the model says, context engineering focuses on what the model sees in one request, and memory engineering focuses on what the model carries from every conversation into every future one. Agents that feel like they know you aren't running bigger models, they're running better memory pipelines. Call to action. Which stage would you implement first? Comment below. By implementing a memory pipeline, you can create AI models that learn from past experiences, retain